All right, so last part of 2008 that I'm going to go through. Part D, the normal boiling point of diatomic chlorine liquid is 238 Kelvin, and it's higher than the normal boiling point of HCl liquid, which is at 188 Kelvin. Account for the difference in the normal boiling points based on the types of IMFs and the substances, and you must discuss both of the substances in your answer. All right, so here we go. So I went ahead and drew the structures, or I didn't draw them, but you would need to draw the structures for each because you're not given them. That's not too bad. Are they polar or non-polar? So Cl2 is going to be a non-polar molecule. The two chlorine atoms have the same electronegativity value. Therefore, the bond is non-polar and the molecule is non-polar as well. All right, HCl. So clearly this is going to be a polar bond and a polar molecule, so it is polar. You have different En values. So a dipole is formed. So the negative end of the dipole is around chlorine and the positive end is around hydrogen. And that's probably way more detail than you need to go into, but I'm just going to go ahead and give that to you there. So the IMFs, because I've got to talk about why the boiling points are different. So again, this is not a solubility question in part D. This is a boiling point question, and why are the boiling points different? So here, the IMFs between the chlorine molecules is induced dipole, and a much simpler way to say that is London dispersion forces, and that's it. It's not polar, so it can't have any of the other good stuff. And then HCl is polar, so it's going to have dipole attractive forces, and it will have LDFs. All right, so the boiling point of Cl2 is 138 Kelvin, and here you're 188 Kelvin. Okay, so then you stop and you think, well, shoot, I know that the dipole forces are stronger than LDFs. But if that were the case here, then HCl would have a higher boiling point than Cl2, and it does not. Something else must be happening. So this is what we talked about in class about polarizability. So I'm going to go back up here and say Cl2, the molar mass of Cl2 is about 71 grams per mole. Again, molar mass does not tell you anything about IMFs, so don't write molar mass. But the higher the molar mass of a molecule, the more electrons that are there. More electrons do not increase molar mass. Electrons don't really have a significant mass, but the bigger the cloud gets, the more electrons that are there, okay? So Cl2 has a larger electron cloud due to more electrons in the molecule. So its LDFs are pretty significant. HCl has a smaller electron cloud due to fewer electrons. I apologize, sorry, I got interrupted. Okay, due to fewer electrons in the molecule. Okay, so now we need to justify why is the boiling point of Cl2 higher even though it just has LDF. So here's our justification. The LDFs in Cl2 are significant and strong due to the fact that this molecule has a highly polarizable electron cloud. This strengthens the LDFs present, and as a result, more energy is needed to overcome attractive forces, and this causes a higher boiling point. So because the cloud of Cl2 is more polarizable, its LDFs are more significant, which means there are more and stronger forces of attraction between the Cl2 molecules. So in order to boil, more energy has to be put in to overcome those LDFs, and as a result, that drives up the boiling point, okay? Despite the fact that HCl is polar, its LDFs are not, okay, sorry. So despite the fact that HCl is polar, its LDFs are not as strong as the LDFs in Cl2, because the electron cloud of HCl is not as polarizable. Therefore, it will have a lower boiling point than molecular chlorine, the Cl2. All right, so that concludes 2008 examples. So again, you've got your two molecules, Lewis structure, whether it's polar or not, then talk about IMFs. So this format was the same. Let me go back up here for all of this stuff. Lewis structure, and then I put boiling point here, but Lewis structure, polar, nonpolar, IMFs. And even with the solubility question, Lewis structure, polar, nonpolar, IMFs. So all of your charts start out that way. For your boiling point questions, after you list IMFs, then I would list the boiling point and then explain the difference in the boiling points based on the IMFs. And so I did that here again for part B of that question. For a solubility question, which is like part A, after you do the IMFs of the solute, you want to do the IMFs of the solvent. And then importantly, most importantly, the IMFs of the solute and solvent combo. So for a solubility question, you want to think about the 3 steps of dissolving. And you want to make sure that you have IMFs listed for each of those 3 steps. And then for your justification for is something soluble or is something not soluble, you want to talk about how the solute solvent IMFs, that combo, compare to the IMFs of just the solute or the IMFs of just the solvent. So that is the way you're going to chart your IMF questions. And you can do this chart also with atomic structure, where you're comparing periodic trends. That may be a good thing for you to do. Use the chart to your advantage. Be organized with it. Make sure you fill in all of your boxes, and make sure that you're comparing what is being asked based on the question. All right, thanks.